Okay, so we go for next presenter, Jelle, and is effect of indoor temperature differences and zoning on the performance of energy efficient ventilation strategy for domestic buildings. Floor is yours, please.
Okay, so good afternoon again, everyone. I'm presenting on behalf of Josue Borrajo Bastero, who was one of our PhD students, but as Hilde mentioned, the project in which this work was done has already ended, and so he was not able, he left our research group and was not able to come here to present this. Most of it has already been included in a paper from the AIVC Rotterdam conference. So if you want to read through it more carefully, you can check out that paper on Airbase and go through the details. So what am I going to talk about? Well, the title is quite long, but it's a very specific situation where we're looking at the impact of not having uniform temperatures throughout the building on the predicted performance of energy-saving ventilation strategies, which include, in this case, both heat recovery ventilation and demand-controlled ventilation, and a combination of those two strategies. To give you a bit of an idea, the quality of this picture is not fantastic, but I guess we'll be able to see what it's about. So we started this analysis a couple of years ago, and this is a picture from a paper that Arnold wrote about this, where we look at buildings that are not one zone buildings, but have multiple zones, of which some are heated and some are not heated. But the central heat recovery ventilation system delivers air to each of these spaces. So in the left picture, you can see the one zone assumption. So the preheated air goes into the space, is then exhausted again, and is used to recover heat to heat the incoming fresh air. In this situation, apart from the correction factors that we heard about a couple of presentations ago, we can assume that the performance will be relatively close to the test conditions of the system. If, however, we have a zoned building, what we get like here, two-zone, this is a simplified two-zone approach. The heated air will be supplied to a heated space, but also to an unheated space. And therefore, the recovered heat from the heat recovery ventilation system that is supplied to this unheated space will increase the temperature of the unheated space, but will not contribute to the decreasing of the heat demand of the heated spaces, or it will do so only indirectly by reducing the heat losses between both spaces. And so this reduces the usable effect of the heat recovery, and this reduction is a function, and this was also described in this paper, can be modeled as a function of the ventilation rate and the losses through the envelope. So this was the starting point. We wanted to expand this analysis to a larger set of energy efficient ventilation systems. So as I said, we started looking at heat exchangers, but then we wanted to also see if this effect also exists in other ventilation strategies like demand-controlled ventilation, where instead of sending the air through every space in the building, you actually modulate the airflow rate based on the demand. And so potentially this spreading of the recovered heat is less. And then, so that would be the last option, where we have heat recovery plus demand control. And then we also wanted to look at systems that only do demand control, where we expected that maybe because you reduce the amount of cold air coming into the unheated spaces, because they're typically unused, you could also have the reverse effect, where you have an additional gain compared to a situation where you had constant extraction in those spaces. To quantify this effect, we relied on simulations, and we defined a method of trying to capture what this was all about by looking at the predicted heating demand of the building in several scenarios. So the baseline scenario is a scenario where there's no ventilation. So then you have certain heating demand that corresponds in essence to the infiltration and transmission heat loss to maintain thermal comfort in the building. Then we had another reference scenario that is a standard ventilation system without heat recovery and without demand control, that provides the required ventilation rates in all the spaces. And then we have the ventilation system that we're considering, either with demand control or heat recovery or both. And so we compare the heating demand from all of these scenarios, and based on that, we can check what the contribution of these energy-saving ventilation strategies is in reducing the heating demand for those systems. And so based on these inputs, we defined a metric, the formula of which you can see here. So basically, we look at the proportional contribution of the energy saving ventilation strategy to reducing the heating demand from the maximum value corresponding to a non-energy efficient ventilation system towards what we think is the maximum achievable reduction, which you get when you have no ventilation. Okay, it's important to note that the reverse actually happens when you look at cooling. So then you need to invert the formula for the indicator, but in essence, the philosophy remains the same. As I said, we based this study on modeling. So we used a Modelica model using these libraries, mainly ideas libraries, and our own in-house developed libraries for ventilation systems to predict the energy demand for the different systems. And then we compared different scenarios, looking at different types of houses in different types of climates in Northwestern Europe, going from Marseille, slightly warmer, to Berlin, slightly colder. And we looked at different occupation scenarios in the dwelling. So a dwelling with only an adult couple, or so relatively low occupancy, or a scenario with a family with children and a higher occupancy rate. I'm sorry, this does not look very good. Well, yeah, sure. So I guess we'll have to restart. Next one. Not again. I don't know. It works fine on my computer. I think we will try to skip the next slide. Well. Maybe directly go here to directly there. Yeah, let's try that. No. Okay, so we skipped the problematic slide. It was explaining the different types of ventilation systems that we looked at. There's over 20 different systems that we considered, including exhaust systems, heat recovery systems with demand control, without demand control. And then we also look at different heating scenarios. So as I said, we're looking at zoning. And so we looked at situations where the whole house is heated to the same temperature, or different zones are heated based on the occupancy schedule, or not only the zones are heated based on the occupancy schedule, but also only when a person is present in that particular zone, that zone is heated. And for all of these situations, we use heating set points that were derived from, not again. I'll just talk and then give you the main conclusions, and maybe we'll have some pictures with it. So basically, we did in total over 60,000 simulations to achieve the results we're looking at. Oh, well, I was hoping we would be looking at, showing that there is an effect of this zoning on the temperature, on the expected performance of the energy efficient ventilation strategies. Yeah, if we keep it like this, yeah, that's a good idea. Yeah, just so.
We try to.
But I can show. No, okay, right, okay, yeah. Right, perfect. So then can go to next one. Yes. Next slide. Same problem. No, but we can show it like this here. If we can switch back to this machine. Don't go into presentation mode. I share the. Yeah, okay. So I hope if we not go into presentation mode, we will actually be able to show it. So what we see here is the result with on the x-axis, the reduction in heat loss, and on the y-axis, the maximum reduction of heat loss. And so you would expect things to be clustered around the nominal efficiencies of the heat recovery or the demand control factor of these systems. And you can see that that's more or less the case, but there's a quite wide variety around those linear lines. And then on the next graph, we're seeing the results expressed as a relation between the test efficiency of the heat exchanger, if there is one, and the indicator that we developed. And you see two things. For a number of strategies, there is a value lower than the test efficiency, which could be described by the 45-degree angle line here. And so this is where this temperature effect, this temperature zoning effect can be seen. And then on the, there's also a number of points that have much higher performance, and this is typically due to the combination of heat recovery with demand control in those systems. Now, so we clearly see that it has an impact on the performance of the systems, the distribution of the air in the dwelling changes the behavior of the system compared to the test efficiency of the system. However, this does not show how big the contribution of the temperature differences as such is. And for that, we used another comparison where we compare our indicator for two scenarios, where the first scenario is the one we've shown results for so far. And then the second scenario is a scenario where we uniformly heat the building to the same average temperature as in the previous simulation, which temperature-wise is equivalent to making a one-zone simulation of this building. And then we do the same analysis for the different situations, so non-uniform and uniform temperatures. We calculate the same metric, and then we divide both results as a ratio. And so this is what you can see here. On the x-axis, you get the result for uniform temperatures, and on the y-axis, you get the results for non-uniform temperatures. And what you see here is that on average, the results are very close to unit. So the ratio is about 1. There's only very slight variations from that. And the variation is biggest for systems that only have heat recovery. So if you look at the graph here, here it's very close to 1. That's heat recovery and demand control. Demand control only is also close to 1. But here the slope of the line through these points is slightly different from 1. And then if we summarize the results based on systems, this is also what we see. So this is what we can see here on the right. For systems that only have heat recovery, the effect is slightly bigger. So you have worse performance of the ventilation system than in uniform conditions if there are non-uniform temperatures in the building. And this effect becomes bigger the lower the ventilation rate is compared to the total heat loss of the building, which is what you can see in these top 3 results here. And this is also confirmed if we're looking at different types of buildings. So the better insulated the building is, so the the bigger the contribution of ventilation heat loss to the total heat loss, the closer the results are to unit again, so the smaller the effect. And then finally, this is also confirmed again by the type of dwelling. So the more compact dwellings, again, where we have a bigger contribution of ventilation heat loss to the total heat loss, the effect is smaller. And so after a roller coaster of technical problems, that was the conclusion of my presentation. Thank you very much for your attention.
Okay, so we have time for questions and discussion, please.
Thank you for your presentation, Jelle. I have a very simple summary. Could you say that as we all move towards zero or almost zero energy buildings, that a one zone approach for residential is just, as in most countries is already done, is a good practice?
Yeah. So that would be a very short summary of a lot of results. Indeed, as you move to better insulated dwellings, temperature differences get smaller anyway. You get closer to uniform temperatures, and so the expected impact of that on the performance of the ventilation system becomes negligible.
Yes, and if you add to that in the renovation cases, very often they are looking for room-based solutions, then it is even more practical to neglect these differences.
Well, there I need some nuance. So we have room-based solutions in in the ventilation systems that we looked at. Typically, they have lower heat recovery efficiencies, and we also see a correlation. So the worse the heat recovery efficiency of the unit is, well, again, the bigger the ventilation losses in the total heat loss. And so there we see a somewhat bigger effect. That's the purple ones. And you see that those are a little more shifted than the other ones.
Thank you.
But to give you an idea, even then, the average effect is on the order of a few percent, like 4 or 5%. So
I know that we had a very good presentation in the beginning. It was heat recovery and so on. So if you have a question for all 4 presentation, please raise your hand. Paul?
So I have a question for the Mitsubishi energy recovery ventilator. It was really very good presentation. I like it a lot. And here you have a hidden moisture transfer, and you use a paper as a material for your heat recovery. Have you documented that there is no any transfer of the pollution between the extracted air and the supply air? And if there is any transfer, what type of pollutants are transferred and at which rate? I ask this question because this type of solutions are becoming popular in Europe as well. The reason for that is that there is again the discussion about the low relative humidity level in buildings, particularly in the northern part of Europe. Despite of the increasing ambient temperatures, the humidity in buildings can drop down to below 30%. And then the question is whether there are solutions that would not require active humidification of the spaces, but basically integrated with the existing or designed or installed ventilation systems that would allow some recovery of the moisture from the air that is extracted from the spaces. So this is one reason why it is interesting for the low relative humidity. The other one is that basically by installing mechanical ventilation, you will increase the moisture removal from the space, and that will drive the humidity in the spaces low. And then finally, humidity was also discussed in the context of aerosol transmission during the COVID pandemic. And so the question was whether increasing humidity in the space would provide benefit of reducing the risk. This debate is going on, but the solution that you presented, where the moisture is recovered from the extractor, can probably provide some information on how we can better control the moisture in the space without necessity for the active humidification. So sorry for my long comments and explanations, but this is what I would really like to learn more about. Thank you.
Thank you very much. 高橋さん、マイク使ってあそこで。
つなげない。
つなげない。
つなげないんです。ブームに入らないといけないので。
なんかカメラで映す。
カメラで映しますか。そこにカメラが。
画面映してやるけど。
このカメラに。
これに。
画面を、
はい。これを持って。
アナログに。
はい。
アナログで構わないから。
すいません。
いい。
機械のこっち側のカメラだ。ここのカメラ。これでもいい。
He is now preparing some slide. Could you wait, please?
カメラはどこのカメラで？このカメラで？あ、すいません。Thank you very much. So several questions. Thank you very much. So our paper-based heat exchanger extremely small. So これを大きくすることはできないでしょうかね。Yes. So our paper-based exchanger sometimes asked this question. So together with the moisture particle, transfer the like a gas or a toxic something or CO2 something, transfer to exhaust side to supply side. Unfortunately, some percent yes. However, we have the like a test data, how much gases, CO2 like ammonia come back to the room, not exhausting. So for example, maybe ammonia is a good example. Where ammonia? Somewhere. Like ammonia, for example, how many percent? 2.5? 2.5? Anyway, you can see. Anyway, ありがとうございます。Unfortunately, couple of percent come back. Do you mind or you don't mind? I don't mind because over 90% of toxic gas like ammonia go out to the outside. Couple of percent come back only. So unfortunately, not zero, but enough satisfied level, we think. So there are some other gases like I cannot see, but gas depends on the gas or particle. Some percent, couple of percent will come back. However, the energy recovery ratio or humidity recovery ratio is much higher than plastic aluminum kind of thing. So I will show you the difference between type and paper-based type in the next page. Is that okay? About the transfer. Thank you. Yes.
I'm not extending the subject. We've been long. This is a long day today, but I think it's a very important topic here. So,
すいませんが。
because of the three reasons that I provided, and so if there is a transfer of some of the pollutants between the extract and supply,
Yes.
would it help that we would increase the requirement for ventilation? Basically reduce the concentration of the pollutants in the space to accommodate for that transfer. So say, if there is a one-to-one relationship and you transfer 10% of ammonia back, so then maybe you can increase your ventilation rate by 10%, you will reduce your concentration, and then basically this transfer will be basically dealt with by keeping the level of ammonia lower in the first place. So when it's transferred back, it should not probably contribute significantly to the emission, to the exposure in a space. I need to make this calculation, whether it is one-to-one transfer, but I just give you an example how it can be tackled with.
Thank you very much. So it's difficult. I have no experience to consider that kind of gas transmission ratio. However, how about this idea? So we talk about the CO2 control to drop down the certain level. For example, CO2. For example, like ammonia or your determination to detect the your index gas level, increase the ventilation air volume to drop down to meet your requirement.
Right.
That's just the idea.
Yeah, exactly. This is what I was thinking, is
Yeah.
that basically instead of 1000 ppm, you would run on 950 or 900 ppm to basically account for the fact that there will be some transport. So then in this way, you will still keep the levels of ammonia and other pollutants at the lower level, equivalent to what you would get at 1000 ppm. But that would require some calculation and modeling. But I think that is the option.
Yeah.
And then probably, what would it have any effect on energy recovery? Because you will then increase the airflow through the through your system.
Yeah.
Would it affect your efficiency?
Yes.
But how much would it affect? Would it increase or decrease? I don't remember now.
Okay. As theoretically, the one unit, I chose, let's say, this unit, say this chassis with heat exchanger, this size. So increase the air volume. Unfortunately, efficiency transfer going down. On the other hand, decrease the air volume lower. So heat or energy recovery efficiency going up. That's theory, you know. In that case, by using the CO2 sensor or whatever, to minimize the ventilation air volume, to maximize the energy recovery, also minimize the running cost of air conditioner because exchange air volume is low. Double effect, we think. So we are always thinking about, in total, as a air conditioning ventilation system, minimize the, let's say, running cost and initial cost. Does it make sense for you? Thank you very much. Thank you very much.
But it requires some modeling.
Yeah.
To account for the effects. Reduce efficiency because of the flow, but at the same time, reduce effect of transfer of pollution.
Yeah, I agree. So therefore, maybe lots of choice or study we need, but make a big, choose a bigger size of unit. That means bigger size heat exchanger, even higher air volume, it can have enough energy recovery %. But if you minimize the air volume with large size unit, extremely high efficiency we can expect. So such kind of like a size, cost, dimension balance we need. Is this okay? Not 100% okay, but thank you.
More questions?
Huh?
Yes.
Sorry, one more question we got about the moisture.
Oh, yeah.
May I reply?
Yes,
いいですか?
Please.
So this is sorry, a winter example. Inside temperature 20 Celsius, 50% relative humidity, comfort, winter. Outside temperature 0 Celsius, like a snow day, winter day. In that case, in this situation, open the window to get the ventilation, natural ventilation, zero energy recovery, and absolute humidity 1.9, dry, come into the room. Less energy, I mean cost. However, sorry, here, sensible heat exchanger without moisture recovery, but temperature, yes. In that case, for example, temperature recovery efficiency 70%, 0% of humid recovery. So temperature 16% good, but absolute humidity is same as outdoor, dry. So we need to add humidity by something, humidifier or something, it's cost. In case of energy recovery ventilator bias, paper base, moisture recovery, enthalpic recovery, not only temperature but also humidity. Thanks to that, 1.9, no, 5.2, similar to room absolute humidity. That means energy saving, no need to add humidity. That means humidifier, no need to work a lot. Unfortunately, we cannot keep the 7.3%, but 5 to 5.3, not 100% okay, but we can save the cost for humidification compared to this and this. Does it make sense? Because we chose the total energy recovery module, moisture and temperature. Okay,
Yes, please.
thank you very much. Yes.
Please turn on the switch.
Yeah, for operation for cold climates. So the technology requires defrost strategy. Does your technology have a defrost strategy?
Very difficult, tough question. That's important. So, to be honest, let's say this loss night energy recovery ventilator can work at -10 Celsius without any problem. This kind of energy recovery we can expect. Okay. However, colder than -10 Celsius, it change into the intermittent operation. So supply air volume, supply ventilation stop with some interval to keep the frost problem of the heat exchanger inside of the unit. Because temperature humidity recovery efficiency is high, so cold climate operation is very tough for paper-based heat exchanger. Wet and freezing and drop the the water might be happen. We need to avoid. Therefore, we have some limitation. Please use this unit -10 Celsius, but protection for -10 with intermittent operation, self-protection control is adapted. And if very cold climate, -15 or -20, like Russian or Northern European countries, even America, we recommend to equip the duct heater, like an electric heater, before the take the outdoor air to the unit for protection. So it's not energy saving against the energy saving issue, but we need to take a balance between, how to say, product protection and cold climate operation. This is the situation. And we know not only our product, others, like a traditional air handling unit with rotary wheel heat exchanger, same countermeasure, a preheater before the heat recovery module. That's our understanding. Is this okay for you? The manufacturer, we want to solve this difficult scenario, but still now difficult. This is a fact.
How much time we have? Because it's more discussion. I think in heat recovery ventilator, I don't know exactly, but in Europe, I think it goes into the winter mode where it's basically needs to protect against the freezing at the lower temperature, at the higher temperature, because I think you recover moisture here. So this is the reason why you can go down to -10 degrees. I can tell you in Denmark, we haven't seen -10 degrees in the last maybe 5 years. So it won't be any problem in Denmark. In Europe, the maps, European maps, I mean, maybe 2-3 days a year. The climatic maps for Europe has moved. I mean, the ambient temperatures actually are much, much higher even during winter period. I have another question also related to the pollution transmission. One thing is that some of the pollutants will be transferred from the extractor to the supplier, but there may be some pollutants that may absorb in the actual paper. And there could be some absorption and removal of this, and then maybe under certain condition, they may be desorbed. This could be one aspect. Then would there be any reason why the material that you use for heat and moisture transfer that can get polluted by some particular type of pollution? So the require that maybe supplier is very, very clean, because it can be deposited particles on it or something like that, dust and so on, which will reduce the characteristic of it and then transfer of the moisture. Did you look at that aspect as well?
Yes.
Sorry for asking several difficult questions.
Okay. So the ventilation loss line unit have filters before the heat exchanger. So upward, outside air, like a polluted air, like a pollen or PM 2.5 or dust or whatever. So most of the particle removed by pre-filter before heat exchanger. That means supply air is basically clean. And we have the optional filter is like a not HEPA filter, but high efficiency filter. Remove the PM 2.5 over 95%, something like that. Optional filter adapt here, so you know, much clean air come into the room. But in that case, maintenance or replacement is necessary. So standard filter, every 3 months, we recommend to clean by vacuum cleaner or something. Also the extract, same pre-filter, originally kept every 3 months or every 3,000 hours operation vacuum cleaner. It's like a essential, how to say, maintenance, regular maintenance. And optional filter, high efficiency filter case need to replace, reuse necessary. Not necessary, sorry, not possible. And also, well asked question is heat exchanger. So the surface of the heat exchanger, some dust may be stuck. So every 3,000 hours or 3 months, 6 months, vacuum cleaner clean, it's okay. So inside of heat exchanger, it's a little complicated structure. However, we have a, let's say, experience over 10 years, 11 years, cut inside, open, basically clean. Thanks to the filter and need mandatory regular maintenance. So we cannot promise you, but original performance, for example, 70% energy recovery efficiency and like a pressure drop, like a clogging. By regular maintenance, we can keep over 90% as against original なんだっけ specification. Maintenance necessary ね。Is this okay?
Whether there will be any absorption of pollutants, gaseous pollutants on because the paper, right? So maybe there will be some adsorption or absorption in the structure of the material. If you looked at whether there will be some accumulation of pollutant, and maybe it also can serve as a air cleaning, you know, to some extent, you know.
Maybe we don't have such a like a
information. Okay, it's
information, but we need to consider, as I told you, we need to listen your voice from the market. Is this okay? ありがとうございます。Yes.
Is it possible to change the defect? I mean, as a material, like filter, so you can change it every year.
Yes, possible, but cost. Yes. So, to be honest, a filter, we have the like a regular, how do you say, catalog thing. But heat exchanger, it's quite rare to replace every 2 years, every 5 years. So most of the case, unit life is, for example, 10 years or 15 years. Most of the case, heat exchanger not changed. 高田さんいいですね。Most of
What's the cost of the
I cannot say, well, I don't know, but it's not cheap.
You can ask cost later.
Yeah. Thank you very much. Yeah, it's like a FAQ, life or durability of the heat exchanger, because I say paper, life may be short. Everyone ask.
Okay,
Thank you very much.
Last question. Microphone.
But I still had a question for Mr. Khan, right, on the correction formula for the thermal effectiveness. Because you said the correction depends on the airflow ratio in the air handling unit and on the net supply air ratio. But these typically depend on the local situation and the ductwork to which the air handling unit has been connected. So my first question is, are the airflow ratio and net supply air ratio then measured for each system to be able to apply the correction? And the second question is, can the air handling unit not automatically balance the flow rates and improve the airflow ratio to an extent that the correction is not needed?
Yes, Dr. Sach, please.
I think you have given two questions.
Yes.
I think the relationship between for example, airflow rate and total effectiveness, and airflow ratio and total effectiveness, and net supply ratio and total effectiveness, their relationship cannot change. It depends upon the product. But by the design, for example, airflow rate, airflow ratio, and sometimes, maybe no, only airflow rate and airflow ratio can be changed. For example, in office building, I think over there is a toilet. And the toilet, they have a exhaust ventilation. So usually, designer of HVAC system take into account that exhaust ratio, exhaust amount of air. And usually they decrease exhaust ratio going through the heat recovery ventilator. You understand? In that case, total effectiveness of the heat recovery ventilator can be reduced. You understand? So those parameters are dependent on the design practice. So we are now recommending to keep the balance between exhaust and supply even. I mean, the ratio should be as much as possible equal to 1 to utilize the performance, energy saving performance of heat recovery ventilator as much as possible. So we are now utilizing that kind of theory and equation and program, integrating into the primary energy consumption calculation program to promote that kind of better practice for designers. And what is the second question of yours?
I think that was an answer to the second question. The first question is that you showed the results of a primary energy calculation for an office building. So is the correction function that applied for each individual building?
For example, as Takahashi-san explained, some product has automatically control the airflow rate by using the function of inverter and DC motors. In that case, it is very clear how to keep the balance of supply and exhaust. You understand? And I think there is one idea to buy larger size heat recovery ventilator and operate them lower switch to make the airflow rate lower in order to get the better effectiveness for heat recovery. Okay.
Thank you.
Yes. Thank you for cooperation. It is time of closing today. Do you have any comments, Dr. Sach? No? Okay. Then see you tomorrow also. Thank you.